Hello, my name is Calvin and I work within the sales organization here at Juniper Networks. And what I wanted to share with you today is a new resource for those network engineers that are trying to get familiar with network automation. Now, what we're doing is we're combining some of the traditional reference architectures for networks from different domains, security, campus data center, etc. We're going to take some of these reference architectures and we're going to combine them with some of the open source tools like Python and Ansible and Nornir and others so that you can see where network automation can actually tie in. Now, in the use case for today, we're going to be focusing on the building and validation of a layer 3 VPN circuit across an MPLS backbone. Now, don't run away if those words don't make sense, or if you're just intimidated typically with service provider technology. Don't worry about that. We will cover a little bit of the networking type of stuff, control plane information, etc. But our primary focus again is the sharing of this network automation concept with you. So what we're looking at right here is the GitHub repository that's going to host all of our Python code for this specific topology. In addition to that, this is also the source for our documentation website. So if I just go ahead and click over on this link right here, I'll be redirected to the site's documentation. It's here that we'll be leveraging the information stored here to help us get familiarized with this specific project. Things like, how is the network composed? How's the IP addressing taking place between the devices? And we'll also be doing a deep dive on all of the scripts that are leveraged within this so that you understand why we're importing certain things into our code, what certain statements actually do, etc., etc. So now that we have an understanding on this specific project and how to leverage the documentation, let's go ahead and begin our journey with going over the network topology. So our ultimate goal for this network topology is to get PC1 to ping PC2. At the surface, doesn't sound too complicated, right? One host should be able to ping the other. Well, the gotcha here is that there's going to be a MPLS backbone delivered by a service provider in between. So you can look at this CE1 as being the customer edge router 1, and the PC is directly connected to the router. And on the far side, we see customer edge 2, also with PC2 connected to it. That's the only equipment that will belong to the customer. Everything else, meaning anything that starts with the letter P inside of the center here, this will belong to the service provider. And the tricky part here is that the service provider needs to build a VPN circuit from PE1 down to PE4. All right, now that we have the basics of the networking taken care of, let's actually take a peek at the lab itself, just so that we can see the state that it's in, what it looks like to execute these scripts, and the state that it ends up in at the end. And once we've completed that, what we'll do is we'll go into the code deep dive. So I'm going to open up my lab. It's in EVE-NG. And if you did not know this, the way that you get past these in Google Chrome is you type in, "This is unsafe." And that will allow you to pass a invalid SSL cert. So we'll go ahead and type in username and password. And what I should see here, yes, okay. So this is the MPLS lab environment that we were just looking at from the project that we had been talking about. So we should be in I'll call it a bootstrap state. What is on here is a username and password, a static route so that I can reach the devices, and SSH and netconf enabled, right? These are the basic parameters you're going to need anytime you interface with a network device. So let's just validate this really quick. I'm going to hop into, let's hop into this one here. And we'll say show configuration, display set, and that's it. It looks like we got a few extra things too. Let's talk about this. We've got LLDP enabled on a series of interfaces. That's cool. That'll help us do things like show LLDP neighbor. All right, so yeah, we can see here. Let's try to move this out just a little bit. And I'm just gonna, let's try that again. Sometimes with even G, if you need to expand the web console, you'll need to actually reopen that console session. So if I said show LDP neighbors, here I can see from router P1, which is this little router over here, we can see that we've got adjacencies to almost every other router in our topology, right? At least all those in our MPLS environment. But other than that, not a whole lot of configuration going on here. Display set, no more. I have only one interface configured. That's my FXP0. It's our out-of-band management that I'm using to actually access this device. Again, a couple of static routes just so that my home network can reach my DMZ, which is where this is located. And that's it. This is not enough to really do anything other than power on and just hang out. It's not going to be able to serve any traffic. No routing protocol is configured. Not really exciting. Just to validate as well, let's look at our customer edge router. I'm going to go ahead and just open this. We'll see if we can get away with that. Nope, I'm going to have to reopen this. We'll pick on router CE1, show configuration, display set, and it looks pretty much similar. Not a whole lot going on. What we also have, though, is we also have two PCs. Remember, our objective here is to get PC1 to ping PC2. So let's check out PC1. And this is such a cool feature of EvenG, the ability to deploy desktop computers within a container environment. Really gnarly. And for some reason, mine isn't loaded. Oh, that's terrible. Well, that's definitely not going to work for us. Let's try to restart. And I'll try PC2 at the same time. All right. Looks like I've got to oh, I've got PC2. It looks like it's working. We'll have to... Oh, no, there's PC1. Okay, cool. All right, so sneak peek, this works. You can tell that I had previously validated this just before we began, but let's try those same commands. I'm going to trace route from 10.0.1.2. I'm sorry, I'm going to trace route from PC1 to 10.0.1.2. That's the IP address on PC2. Let's just validate that really quick. This should not work. If it does work, I've got some explaining to do. IPA, we're going to say grep 10. All right, so it looks like my IP address is on ETH0, and the IP address is 10.0.1.2. Just perfect, right? But can I get there from PC1? Well, spoiler alert, this is going to fail. And it should fail at our very first hop, which that's kind of what we're seeing here, right? We get all stars coming back from all of our hops, which tells us that the trace route is effectively not going anywhere. And the reason it's not going anywhere is because, well, the CE route, all the routers are not configured outside of the bootstrap. And I'll just try to ping my default gateway just to prove this on this side. IPA grep and say inet. My address on PC1 is 10.0.0.2. So my, let's do IP route. My default route is 10.0.0.1. You see that right there. So can I ping my default route? 10.0.0.1. And I cannot. The reason I cannot, you already know what I'm going to say. The default router is not in a configured state. Show configuration interfaces. The only interface configured is the management. So my pings are going to die. My routings are going to die. Everything is effectively dead. So we're in a good starting spot for our scripts execution. But this, again, if you've never seen EvenG before, this is what it looks like. It's a virtualization platform. Allows you to do some really incredible things. This is an amazing product. Let's now perform all the automation that we're going to go over within our code deep dive. But let's do it from a new perspective. I'm sorry, let's start completely from scratch here. I'm going to move into my directory var/temp. This, if you've never known, var temp is just a temporary directory that gets flushed whenever your computer reboots. So I like to use it as kind of like an ephemeral place to host any of my projects. In this case, our GitHub MPLS project. Now what I need to do is I need to come back to my repository here and click on this green button and say I want to clone. We'll just clone it over HTTPS. And we'll say git clone and type in or paste in the URL. And that's going to reach out to GitHub, grab the latest copy of my project and store it in a local directory here that we should now be able to see called Juniper MPLS L3 demo. So great, we've got the project files available for us now. Now, your terminal might look a little bit different. I'm using a theme, a different type of shell. So don't worry if what you see on your terminal, whether it's Windows, Mac, or Linux, looks a little bit different. I just personally obsess over the aesthetics on some of these things, and so that's why I try to make it look a little prettier. All right, now for us, we're going to say again, what we need to do is we need to activate our Python virtual environment. What we have provided in the project files is two different ways of executing this automation. We're going to use one. The two different ways is we have a Python virtual environment that's able to be installed by using a tool called Poetry. And we also have a Docker container as well, if you'd rather issue these within Docker. I'm not going to get into the Docker stuff because it's a whole other video. We're not going to go down that route. Instead, let's just talk about using the Python virtual environment. Now, I can tell you if I was to execute my Python scripts right now, they're going to fail. And let's show you exactly what it looks like and why it's failing. I'm going to change into the directory that holds my Python files, which is files/Python. And I'm going to say Python configure.py. Excuse me. Now, I get a message come back saying there's some invalid syntax. And this is kind of indicative of the problem that we've got. It's not exactly the right error that I wanted to showcase here, but effectively there's a problem with this. What the problem is that if I don't specify where our script's Python environment is, then the computer's going to default to its own instance of Python. We can validate that by saying which Python. Now, what's really cool about this command is it's effectively saying, hey, computer, in my case, it's an Apple computer. If I was to execute Python, which version would you execute? You can have multiple versions all over the computer. If I hit enter, I get back from the computer, it says, I'm going to execute Python from /user bin Python. That belongs to my system. All right, so here's the issue. I need to have a safe space for all of my external packages, things like Juniper's PyEasy, which we're going to be using for this project, Jsnappy, Paramico, all these other all these other Python libraries. I need a safe space for them to execute, and it sure isn't user bin Python. So again, what we've included is a tool called Poetry. There's a link inside of the documentation if you'd like to figure out how to get started with Poetry. But what we'll do is we'll say Poetry install. And that's going to look inside of the root directory of our project from GitHub. And it's going to be looking for a specific file called pyproject.toml, which is effectively a set of environment configurations on my computer that I had checked into GitHub. And one of those configuration objects is list of all the Python packages we need for this program. So when I say Poetry install, what's going to happen is that my local computer will execute Poetry and create a virtual environment to which Poetry will install all these all their Python packages into that virtual environment. So in the matter of time it took me to explain that, roughly 38 seconds here, we have successfully created a Python virtual environment. Now, really important to remember, This does not put you in the virtual environment by default. If I hit which Python again, I will still see it saying user bin Python. We've only created the environment. Now we need to activate it. And the way we do that is we type in poetry shell. Now that's going to give us a message here that says we're spawning a shell within this really long directory. Basically our new Python virtual environment that Poetry had created for us. Now if I type in which Python, I do not get user bin Python. I get the path to our virtual environment. And I can validate that all of my Python packages were successfully installed by saying pip freeze. And I can see that these are the Python packages that are activated inside of my current environment, which is in the virtual environment. The ones that I really care about, actually, we really care about all of these, but specifically for demonstration today, it's going to be the Junos EZNC, which is like saying Junos easy way of performing netconf, right? Junos EZNC is the PyEasy package from Juniper. Also, Jsnappy is really important. Jinja 2 is going to be heavily used here as well. And a bunch of other stuff. Let's not focus on that just yet. But effectively, we can now have confidence that we are inside of our Python virtual environment on our computer. Now, what I'm going to do is I'm going to clear the screen here. And let's go ahead and take a look at our files inside of the Python directory here. And we can see right away that we've got a couple of subdirectories. These will each host their own specific files, and we'll talk about them in the code deep dive. But for a high level, configurations is where all of our configurations are going to be stored and downloaded. Templates is where all our Jinja 2 templates exist. Test is where I have a specific test for this project to execute, specifically for Jsnappy. And then the vars directory is where we're going to have our routers configuration variables stored within. All right, cool. Just to take a sneak peek at what this looks like, let's say control level 2 or tree. So again, this is what the configurations directory looks like. This is what our templates directory looks like. We can see that we've got several different Jinja 2 files here. The vars directory should be a barren wasteland. Well, outside, of course, of our device variables itself. So hopefully that gives you a little bit of understanding on how the project is structured inside of the files/Python directory. Let's hit LL again. And what I want to specifically look at here are the Python scripts that we have, right? So we have, how many is that? 5 different Python scripts that each services a different function. We also have an inventory.yaml file. Let's take a look at that really quick here. So the inventory.yaml file is the way that I've created this, I guess this context of inventory. It shows that we have 2 different groups. One group is called routers and another group is called PCs. And inside of the routers is where we're going to be doing all of our automation. The PCs are good to go. We don't need to worry about them. Now for the routers, we see basically the host name of the device and the IP address of the device. This is really important because when we execute, I think all of these scripts, they're going to pull in the inventory.yaml file. And that's how Python's going to know, how do I get to this device? What's its name? What's its IP address, etc. So inventory.yaml is a really important file here. Now, let's first talk about the configure.py. This is going to effectively build the configurations, the full configurations for every one of our routers and push them to the device, perform a commit check and a commit a commit operation that will take them out of the candidate configuration into the running configuration. So what that looks like, we'll say python configure.py. Cross my fingers. Yeah, here we go. Okay, so now we see that we're connecting to a device. In this case, we're connecting to the first router, CE1, and we're pushing the configuration that we generated through our script. And what we get back is a diff, what has changed on the device based on our Python script. So just like you would get on a Juniper router, you get pluses and minuses to show you what's been added and what's been removed. We actually get that back into the console as well. So this should just take about 20 seconds or so for us to complete. So let me just go ahead and hit pause and use the magical power of time warp to get to the end of this execution. Stand by. Hey. Hey. That's all good, devil. All right, it looks like we have successfully pushed all of our device configurations. It took 1 minute and 53 seconds based on this timestamp. Now, let's talk about this just briefly. This project is just a proof of concept that I'm using to help an educational purpose, right? I want to share with you all how automation is actually taking place. I mentioned that because we aren't doing anything threaded and we aren't multi-processing at the same time or either. Basically what I mean is the way Python is going to execute is it's going to tackle the first device first. When it's completed with that device, it will loop over into the next device and then loop and then loop and then loop until it's completed all the devices in our list. This is not what you would do in production. Typically, you would use threads, which would allow you to have simultaneous execution against multiple devices at the same time. But unfortunately, that's a little bit of an advanced topic and just not worth covering here. So I say 1 minute and 53 seconds to build an entire MPLS service provider network and customer router network is pretty darn cool. All right. So now we executed the script. If we execute it again, let's just go ahead and do that. What you'll see now is that we get the none message back from the device. This is effectively saying, hey, look, we're running the script again, right? We're building the full configuration, but the device is telling us that there's no delta. There's no delta. There's no difference within what's being proposed from our Python script and what's on the box right now. So this is just going to loop over our devices and, again, report back that nothing to see here. Carry on, carry on. And so what we should be able to do now, once this is done here, is jump back into our lab environment and be able to see a successful ping and trace route across the MPLS backbone. Back in Eve and G, let's log back in. And I wonder if we'll still have our desktop console up. We do not. All right, let's open that back up. Please. There we go. Now I'm going to test it end to end before even checking out the router configs. Just because I have that level of confidence that the Python script executed successfully. There we go. Okay, look at that. We got some active pings coming. Okay, those pings are from our default gateway. So we started getting pings back just about a minute or two ago. And this was, remember, this was us on PC1 pinging the default gateway, which had previously been unreachable, but now CE1 is configured and we're getting responses. Let's do the trace route now. We're going to trace route to PC1 to PC2. It's taking a little bit. Thanks for your patience. There we go. All right. So hit our default gateway. Then the next hop should be the MPLS PE router. And then we get no information about the MPLS environment, right? Now there's an option on the Juniper configurations to enable a trace route to report within the MPLS environment which router it's currently responding to. But by default, this is for a lot of reasons, but by default, this is disabled. And so what we get back here is, again, the PE router. So this is, I'm sorry, let's go through the hops. First hop is 10001, which is our default gateway. The second hop is this public IP address for our PE router. Then we got no responses coming back here as the packet was switched through labels across the MPLS backbone. But what we do know for a fact is that it arrived on the interface of 216.227.255.2. I just happen to know on top of my head that's this IP address on this interface. So this was router PE4. The .2 is this interface. The .1 is this interface for CE1. And then we get to the end destination of 10.0.1.2. Just again, a ping just to validate end-to-end connectivity. Looks like we're good to go. Really happy with this. Now, we have another way of validating that this is successfully deployed, right? You typically don't want your users to tell you whether or not the network is working or if it's broken. You want to own that responsibility and fix it before they see it. So what we'll do is we'll come back to our project here, and I'm going to run a different script this time called Python validate. There we go. Python validate.py. And we'll make sure to go over this just in a little bit when we do the code deep dives. But what we're effectively doing is we're using another Python library from Juniper called Jsnappy. And this will actually run certain commands on whatever router we tell it to and validate that the output is exactly like we expect it to. In this case, I'm validating two different routing tables on my provider edge routers, PE1 and PE4, the two routers that face the customer environment. And we're making sure that there's routes in the BGP L3VPN table, which is the layer 3 VPN table. And then we're also making sure that there's routes in the customer VRF, which is called customer 1. Not very original, but we're performing these tests on both routers and we get back green for yes and red for no. So really, really great way of validating the state of the environment. Now, if I wanted to, let's do Python rollback.py. And what this will do is this will actually remove our previous commit to the configuration database. It's rolling back to the previous state when we just started this lab. And so this will effectively take us back down to a broken state. So our pings should fail. All the BGP routing tables should go away. Everything should be back in that vanilla bootstrap state. And what we'll do now is we'll run that same validation script against our effectively bootstrapped environment. And I'm getting passes back. What did I do wrong? What did I do wrong? Did we not roll back the config? Let's try this. Let me ping. Yeah, we did not roll back the previous config. Let's look at the rollback here. And don't worry if you don't recognize any of this, if it looks foreign to you. We'll cover this in our code deep dive. Let me see what the rollback ID is. It's currently set to 1. Let's go onto a router and figure out which rollback ID. I guess there was an additional configuration commit somewhere. Let's say show compare rollback 1. Ah, nothing. Rollback 2, nothing. 3, okay. All right. Just between us, I'm going to change this ID to 3, and this is going to execute. I don't know what I did. I think I have a extra configuration commit operation that's taken place. Oh, this is going to fail on PE1, right? No, that should go through. We'll see. PE1 might fail because I'm in the configuration database right now, but we'll see. Actually, let's just go ahead and exit just to prevent any issues. So this should really break it this time. We'll check it out. So what I'm thinking happened there is, although I ran the rollback script, the rollback was, the ID was set to 1, which is typically what you exactly want it to. But I think I have something else that's going behind me and doing a configuration check on the routers. After I configured it, it actually goes back and does another configuration check, which then increments the configuration database. So we'll see. Oh, that's right. That's right. That's exactly what happened. Remember, we ran the Python configure.py script like multiple times. And each time that we did that, that created a new state of the configuration database. That's why it's all goofy. All right. Let's look at the PE router 1 now. Show configuration display set. Yeah, we're back to that bootstrap state. So now if we run the validation script, validate.py, now this should be completely broken, and it is. And Jsnappy has no qualms about throwing a bunch of red on the screen to let you know that, yeah, it's not working like you say it is. So one last script that I just want to go over here. Let's look at which one? We've covered configure.py, rollback, and validate. Let's also talk about generate really quick. So the configure.py script is going to build the configuration line for line, push it to the remote devices, and commit it, just like what we saw. Excuse me. Generate.py is a script for those of you that don't have access to the lab environment. You don't have even G, you don't have access to Juniper VLabs, but you still want to actually see the Python script do the thing that it does. Generate.py will not use PyEasy, it'll just use the Jinja 2 library instead to generate the configurations and save them to a local directory. We'll go deeper on this inside of the code dive, but for now, let's take a look at the configuration folder yet again. So let's look at configurations, generated. All right. So here I can see that we've got a configuration file for each one of our routers. Let's go ahead and delete those. Remove, let's say configurations, generated, and star. And it's asking me if I want to delete all the 8 files. I say yes. And if we look into that directory again, it's going to be empty. All right. So now we'll just say Python generate.py. And just like that, it built all 8 configurations again for us. And if we look into that directory, we've got those 8 files. If we just take a sneak peek at one of those, generated, let's look at the PE1 config. Here you can see these are the set commands that were generated by our Jinja 2 template that actually does the configuration for our routers, right? The difference here is that we're saving the output to a local file rather than actually pushing it to the device. But thumbs up, pretty cool stuff. All right, so that's generate.py. The last one is let's see, clear the screen. The last one is download.py. And bonus points to you if you can figure out what download.py does. We'll see. Yes, we are downloading the configurations to, again, within the configurations folder, this time in a different directory. This directory is called configurations. Was it downloaded? Yeah, there we go. And what's really cool about the download.py script is that it will download the configuration in the set commands, like what we would be typing in from the command line. And it also gives you the standard Junos config output. And to give you an insight on that, we could say configurations, downloaded text, and look at ce1.conf. Let's look at PE1 since we looked at the set commands for that one earlier. And here you can see the actual set commands that are taking place. I'm sorry, the text file from the Juniper device here. Now, you might see a little bit of red and squiggly lines. Don't worry about that. This is just the text reader that I'm using. So don't lose any sleep over what's happening on that side of things. All right. So we've looked at the Python scripts. We've executed all 5 of them. Good job. It looks like our environment. Well, let's go ahead and reconfigure things for right now. And in the background, I'm going to open up another terminal session here. Is it Control-Shift-D? There we go. All right. And what I wanted to now bring our attention to within the var temp Juniper MPLS demo, there's another directory here that holds all of our Jinja 2 templates. And let's take a look at that. Tree, L2, color, and templates, right? Files, Python, templates. All right. So here are the Jinja 2 files that these are effectively the templates that all of our variables will be ran through. We'll take a look at the variables in just a second, but for right now, I wanted to bring our attention to the actual Jinja 2 templates. The trick here that I did is I'm only referencing one Jinja 2 template, which is Junos.j2. Let's take a peek at that one right here. So files, Python, templates, Junos.j2. And this is the Jinja 2 file that effectively will render the full configuration. But what it actually does is it says, if you see a variable called configuration.system, then I want you to run this template, all right, and then exit. And if you see another variable called configuration.chassis, run this template. Effectively, this is the way that I'm building each stanza of the Juniper configuration. So you can think of Junos.2 as kind of like the orchestrator of all the templating. Well, and that's not effectively right. It's basically the orchestration file to say, if you see this, run this template. If you see this, run this one. If this and that one, this and that one. And that's how we ultimately end up with the generated configurations. Let's look at one of the actual Jinja 2 templates, though. Let's look at interfaces, since that's something that everyone probably knows. Okay, but really quick, back up here, our environment should be back up and running. We'll just do the validate pi yet again. Get thumbs up. We got thumbs up from Jsnappy. It looks like our environment is working. I'm going to exit out of that session or that terminal here. And let's clear the screen. And let's look at the interfaces.j2 Jinja 2 file. All right. And so this is our full Jinja 2 template for the interfaces. So if the variable comes through, if a variable is passed into the Jinja 2 and it's configuration.interfaces.interface, then we're going to run these types of commands, right? So this is how we build each part of the configuration. We have this big template file, Junos.2, which references other smaller templates that will ultimately lead into the full configuration when we execute. Now let's look a little bit into the, let's see, L2 color, the vars directory, file, Python, vars. All right, so every router that we have has a dedicated variables file. And let's take a peek at, we'll just keep looking at PE1 since that one's got the most interesting configuration. Files, oops, vars, PE1.yaml. All right, so this is the YAML file for PE1. All of these variables will be ran through all those Jinja 2 templates that we had seen, right? And the top level dictionary will be called configuration. You'll see this more when we go into the code deep dive, but it'll be configuration, then .system, configuration.interfaces, configuration.routing instances. And these will be the variables that pass through the Jinja 2 template, and boom, out comes the actual configuration file. That is true for both the configure.py and the generate.py. Again, the only difference between those two, configure.py will use Juniper's PyEasy to do the templating on the device, on the actual configuration, commit it, validate it, all those things. Whereas generate.py doesn't use PyEasy, it just uses Jinja 2 to generate a local copy of the file. All right, now with all of that said, I think we're in a good state now to where we can actually transition over into the code deep dives back in our project repository. So let's go back over here. Let's get a little bit more information about the network before we dive into the automation. I'm going to start here at the Getting Started page. And from my left-hand side navigation menu, I'm going to look at my networking information. Here we can see an overview of the network topology. In this case, we're looking at our lab from the context of Juniper VLabs. So I should have mentioned this before, but we have compiled a dedicated lab within Juniper VLabs for this topology. We have also included a local version for anyone using Eve NG. So two different lab environments have been provided for you, just in case you actually want to get some hands-on with this. But getting back to our lab topology here, we can see our overview of our network diagram just represented in a different topology. If we look at the IP address schema, let's talk about how the IP addresses are used within our configurations. Effectively, what I've done is I've created an ID that I associate to a router, right? That ID is a numeric number, so like 11, 12, 13, 14, etc. I then use that ID number as kind of the basis for things like a router ID or the point-to-point connections. And so I'll give an example here. Here we're looking at router 1, right? And router 1 could be any of the routers on our topology. We'll just pick one and say it's router 1. Now I've associated the ID of 11 to router 1. Again, it could have been any number. I just went with 11. That means its loopback ID is going to be 192.168.255.11. Its router ID will then be the same as the loopback, which will be, again, 192.168.255.11. But we'll also use that ID when we're building a point-to-point connection to an adjacent router. So router 2 would have a ID of 12. So the way that the IP address schema would go 10.router1, which is 11, router 2.11, and then my local address in this case would be .11. Now on router 2, its connection would be 10.11.12.12. Right. It's one of the nice things about using a /24 is that last octet is there to play around with, and using this idea of an ID as kind of the genesis for all the connections, not only loopbacks, but also point-to-points, really helps us keep things pretty simple to troubleshoot, right? Like when we're looking at a trace route going through the environment, you can clearly see it went through on this link, went through 10.11.12.11. So I know that was the connection between router 1 and router 2, etc. So I hope that much makes sense. The IP address schema is not really important unless you're looking to build this yourself or test it itself, and you're just kind of interested in it. That's the format that I've selected here. Now moving on to the MPLS configuration. Just a high-level overview of what's actually happening here. This is not an MPLS deep dive, unfortunately. Again, if we try to go that route, we'd probably lose out on all the automation fun stuff. But some high-level things to know. The way that we've decided to signal our labels to our neighbors is we're going to be using the LDP protocol for that, right? Not the RSVP. We're going to be using LDP for that signaling. It just makes things really simple. And this, again, this is a small service provider network. It doesn't need to be overly complicated with traffic engineering. We'll never get out of this video series if we go down that route. So again, we're going to be using LDP, and we need to configure that at the protocols level. Also, while we're there at the protocols level, we'll also have to configure MPLS as well. And we have to enable MPLS on an interface, right? So the way that this will happen is that the generated config that we will compile through Python will have an idea as to which interfaces are MPLS aware. It'll use that information to build not only the local interface config, but also the protocols. We need to make sure that we're enabling this on the right interfaces, right? Both MPLS and LDP. If you forget one or the other, the whole thing will break. So need to make sure that that's done right. Additionally, for the route distinguisher, again, we're going to be leveraging that idea of an ID. Whatever ID we associate to a specific device will then help us match the pattern for our route distinguishers. We will only see these route distinguishers on the 2 PE routers that are participating in the VPN circuit. But you'll note that the last octet on the IP address side will be exactly, it'll be its router ID, which was again tied to this idea of an idea that we had associated with it. And for the route targets to handle the importing and exporting of routes, we're going to keep things really, really simple. The target is going to reference the BGP autonomous system number as well as the customer's ID, not the router ID, just the customer ID that we establish here back in our route distinguisher. So hopefully that makes sense. This was a crash course on MPLS, at least the things that you need to have configured. Perhaps we'll have some time to actually dig into more of the meat and potatoes. Now, moving into the routing side of things, we kept things really simple. Again, we're going to be using OSPF as the routing protocol within the service provider environment, and the connections between the provider edge and the customer equipment, we're going to be using external BGP. This is a very, very common deployment mechanism or design where you see external BGP being used to form adjacencies between customer and service provider. A lot of good reasons for that. We won't get into it just now. We might get into it later on, but for right now, let's just check out what's actually generated here within the MPLS service provider environment. We're going to be configuring OSPF area 0, and we're also going to make sure that our loopback is included in there. We will, again, on the provider edge routers, we're going to be performing an external BGP adjacency to the customer, and we're going to be doing that within the context of a VRF. And between the two VPN endpoints, right, between PE1 and PE4, we will have another BGP adjacency, this time using internal BGP, so that we can signal the unicast routes that we had learned from the neighbor routers, right? So router 1 or PE1 will have a BGP adjacency to CE1, and it'll stick those routes within its routing instance, its VRF routing instance, and it'll share that to PE4, which in turn will share the routes it learned from CE2 router. Again, not a MPLS crash course, so we're not going to spend too much time on this. But for those that understand the technology, this is the design that we have for our network topology. I'm sure that most of you will agree it's a fairly simple MPLS layer 3 VPN circuit. The first script that we're going to be looking at is the script, the configure.py, which will handle the configuration of our devices configurations. It'll push it to the remote devices, it'll confirm it, and then commit it into the from the candidate configuration into the running config. So again, all of our Python scripts are located in the files/Python subdirectory, and we will be looking at the configure.py for this example. Let's first cover the different modules that we're going to be importing into our scripts. The very first thing you'll see is we're going to run the import YAML on the top of our script. This will allow us to import from the Python standard library the ability to interact with YAML files. This will be important. As you recall, our inventory.yaml file defines our devices, their host name, and their IP addresses. We want to be able to import that as a instruction or set of instructions on how to reach these remote devices. So that's what the import YAML's for. From juniper.junos, we're going to import the device functionality. This will allow us, or the Python class, this will allow us to define our device with the parameters, things like its IP address, username, and password. The device object will also have several different functions that will allow us to build the remote netconf session over SSH to their devices. A device will handle all of that for us. So a really, really important component in this case. And the config object as well, or the config class, we're also importing from Juniper's PyEasy. This will allow us to handle the configuration, the templating, the pushing of the config, etc. In addition to importing some of this functionality into our script, we also need to tweak a few things. We've got a few parameters that we need to adjust, either to override some defaults or just to create our own parameters. So let's take a peek at that. The first thing is we've got our configurations. Now remember, we imported the YAML library, or the YAML package from the Python standard library to allow us to ingest this inventory.yaml file and produce a Python dictionary for us. This will allow us to, again, loop over all of our devices, and we'll have the IP address and the host name of that. So the way that we're doing that is we've got a dedicated function set up for this. We've called this function inventory, as you can see here. And what we're doing is we're using that YAML package that we imported, and we're loading a file called inventory.yaml. Right. So what happens when you use the safe load method, you're actually passing in a parameter. In this case, we're saying we want you to open in the inventory.yaml and store that object, store all the contents into a new object called devices. And it's devices that will actually return. So anytime inventory is ran within our script, it will return an object called, in this case, is called devices, and then we can set that equal to whatever we need that needs to ingest our list of network devices. Then let's look at the main functionality here, right? So we've got a function, it's literally called main. It's passed in an object called devices, and yes, this is exactly what we had created up here. So we're passing in the list of our devices as a parameter into our main function. This will enable us to have access to that vital piece of information. Then you see us perform a loop over each device within our list. So we're saying for every device inside of the routers group, right? We don't want to loop over the devices from the PC group in our inventory.yaml file. We just want to loop over the routers. So we're going to loop over each one of the routers in that list, and we're going to call in that device class that we had referred to at the beginning of our imports, right? This is coming from Juniper's PyEasy library. This device class allows us to define basic parameters of how to build a connection to a device. So in here, we're going to pass in the host object, and we're going to set it to the IP address that was within the YAML file. That's what you see us doing here. Remember, in this case, we're looping over each instance inside of our inventory file, and we're referring to that instance as the word each. Right, so for each, now we're calling an object within each. In this case, we're looking for the IP object within that list. Now, additional to that, we also have to pass in our username and password. So here I'm passing in as just a string. My user is JCL user, and the password is Juniper !1. And we're also passing in an additional parameter, something here called gather facts equals false. This will basically prevent the Python PyEasy library from trying to gather additional information from the device. That information is really great, but ultimately it does slow down our script. So we're just going to leave this as it is. Now, once we have all those parameters defined, we're going to store that object as a new object called dev, or short for device, if you couldn't pick that out. And then we're going to run this open method on our object. So now PyEasy is going to open a session to this device based on these parameters, the username and password and the IP address. Right. So now we have an active open session to the router itself. All right, and we reward you in this case, but just by printing out to the console a message saying we are currently connected to the router's hostname. Right. Remember, each is coming from us looping over this list of devices from our inventory. And inside of that inventory, there's a field for IP and there's a field for name. Let's go back and validate that really quick here. Back in our code, what we can see in the files/Python directory here, files, Python, inside of the inventory.yaml, you see we're looping over all of these devices that fall within the routers group. That's what the for loop is doing. And each device has a name and it's got an IP address. And that's how we're referring to these within our Python script. Here, we're just printing out to the console, hey, we're connected to this host name. And in here, we're using the IP to form the actual object that's used for the SSH connection. All right, great. So we're connected to the device and we've printed a message to the console to say, hey, we're connected to the device. The next thing for us to do is to create a new object that is a Python dictionary. Now, there's a couple of ways of doing this. And by a couple, I mean there's probably a lot. But in my case, I'm going to say, let's create a new object called data, and I want to set it equal to a dictionary. This will create an empty dictionary. Now, if I really wanted to, I could have also said data is equal to open and close parentheses. That would have done the same thing. It would have created an empty dictionary. I just typically prefer to do things like this because then I could say ls or a list, or I could do a string or an integer. It's a little bit clearer for my eyes. Now, the reason why I'm creating a dictionary to begin with, an empty dictionary, is we need to start stuffing some data inside of this dictionary, right? We need to start, in our case, we're going to load all the variables for a device. We're going to load it and then store it into this dictionary. That way we can call it whenever we're looping over our, or we're running the variables through a Jinja2 template, right? So I need to pass Jinja2 an object. And in this case, I'm saying I want to pass an object called data, and inside of there is going to be another nested object called configuration, and that's going to be equal to all the variables within a specific file. Now, in our case, that's going to be a file located in the vars directory. It's going to be have the name of the router as its file name, and the extension will be .yaml. So in the case of router PE1, let's go back up here and check out what that looks like in our vars PE1.yaml file. Back up here in Python, looking in the vars directory, and we'll say PE1. These will be the variables that get ingested by our Python script, and these will be the variables that we run through our Jinja2 template. Now, if you're familiar with the Juniper configuration, you'll start to look at this and you'll say, that looks pretty familiar. That looks exactly like how I would build a Juniper configuration, right? In that I've got these stanzas called system and interfaces, and another one for protocols. And you're right, that's effectively what I've done. Is I've taken the Juniper configuration data model and I've just translated it into YAML, and that's what we're going to run through the Jinja2 template. I do this for a multitude of reasons, mostly because I don't want to have to build the data model myself. Second of all, Juniper is inherently data modeled, so why not just go ahead and leverage what's already been done? The third is that it makes it easier to understand for anyone that's operated a Juniper device. You know that the host name is underneath the system stanza. You know that the interfaces config is underneath the interfaces stanza, etc., etc. All right, so again, what we're doing here is we've created an empty dictionary called data. We've created a sub object in there called configuration, and then we've set that equal to the contents within our file. So we're effectively loading all of our devices variables from a YAML file, and we're storing them inside of data configuration. Great. Now what we're going to do is we're going to, first we need to attach into the device's configuration, right? So the way that we do that is we use this config class that we had imported at the top of our script, and we're going to pass it our device's our device's active SSH session, right? And then we're going to store an instance of that into a new object called configuration. Now, it doesn't need to be called configuration. I can call this Raekwon the chef. It does not matter, right? It's just I'm trying to be a little bit helpful to understand what we're doing here. We're pulling in the method or the class of config from the PyEasy library. This is going to have a bunch of utilities for us to manage the device's configuration. I'm passing into that the actual SSH connection that we have to the device, and then I'm storing that as an object called configuration. Now that we've got this configuration instance loaded in memory as configuration, what we're going to do now is we're going to load our variables and run them through the Jinja 2 template for our device's configuration. And we want to tell the device that the output here will be in the set format. In contrast to set, you could say the format would be text, and that would be the standard Junos config stanza. You could also say XML. You could also say JSON, right? Just make sure that whatever you pass in as the format is actually what you're generating with your Jinja 2 file. In this case, the way that we perform this is we say the template path points to a directory called templates, and the main Jinja 2 file will be called junos.j2. Now I'm also passing in my template variables or template vars, and I'm setting that equal to data. Remember, data lives right up here, right? We had just created the data object. Remember, data with the configuration object inside of it is equal to all of our device's variables. This will allow us to reference them inside of our Jinja 2 template. And the output here is going to be equal to set. At this stage, we've compiled the configuration and we've pushed it to the remote device, but we haven't actually committed it to the running configuration. It's still in the candidate configuration state right now. And the reason for that is we want to perform a couple of extra functions on the device just to make sure that we understand what's about to change. We also want to understand, does our configuration pass the candidate configuration check? And then, only then, if it passes all of those checks, will we actually commit our configuration on the device and then exit out of our script. So let's see how that's done using this Python package called PyEasy. Now, if you recall, our configuration object is what is represented by our device's configuration. We had inherited this from the config class, which we had imported from the Juniper PyEasy library. Now, because of that inheritance, we get some additional functions that are built within that class object that we can actually call. And what I mean specifically is we have the ability to print a diff to the screen. We have the ability to perform a configuration check. We have the ability to roll back the configuration or commit the configuration. Right? There's all of these additional functionalities were actually given to us when we had inherited that configuration object, which is it's just another reason why working with Python on Juniper devices is so easy, because some of the really common tasks that you would use from a network operator's perspective are available to you here within Python. So the very first thing that we're going to do is we're going to run the pdiff method. This is what gives us the ability to print any diff to the screen. And what's really great about this is that it's not going to just print the actual configuration. It'll add a plus or a minus sign next to the configuration object, just like you would expect from the command line, so that you actually get what was added, what was removed, in clear context within the configuration. After we print out that diff, we're going to run a configuration commit check. This is exactly what it sounds like from the Juniper command line. You would perform a commit check operation. It will validate that your configuration is not breaking any rules and is a actual valid configuration. If that passes, meaning like if we get a true response back from the config check, then and only then will we actually commit our changes to the from the candidate configuration into the running configuration. Now, if we got a false, then we're going to run into the else statement, right? Because the first line is we checked if it was true. and then we would perform a commit. If we actually got a false back, then we're going to hit the else clause within this if statement. And that says to perform the rollback functionality, right? Which will effectively discard any changes that we had staged within the candidate configuration. Now, either the commit operation takes place or either the rollback takes place, we are still going to gracefully close our netconf session to the device. And we're going to reference the device object for that, which has a method called close, which does exactly what it sounds like. It closes the netconf session to the device gracefully. Now, down to the initialize. This is a common question for newcomers within the Python space. Once you start, kind of getting your grasp as what's a function look like, what does a variable look like, what does a list look like, you're ultimately going to run into this statement that's within your Python script, and you say, what the heck is going on here? There are many really great explanations on Google, on Stack Overflow as to what this actually means. Some will give you really technical information that honestly, even I don't get all the time. Some of them will be really high level and kind of simple. I'm just going to leave it at this. You want this in your script. That's it. You want this in your script. And this will be the kind of initialization of your Python script. So all of the functions that we declared above, like the inventory function and the main function, we're going to call those inside of this if statement right here. And that's going to actually be the execution space for our Python script here. As you can see, the very first thing that we call the inventory function, and we set it. Any object that is returned from that, we're gonna store that output in a new object called devices. And then once we have the devices object, we're gonna pass it as a parameter into the main function. The main function is what we just covered, where we actually template the configuration into set commands based on a file of variables, and then we push it to the device, etc. And that's gonna be the initialization part of our script. That will be what actually takes place here. So from a workflow perspective, what this actually looks like, again, you want to make sure that you have your Python virtual environment activated or you're working inside the Docker container, one or the other, right? We've provided both for you, but just still up to you to choose your own adventure. What you're going to do is you're going to change into the directory that hosts our Python files, which is files/Python. And to run this configuration script, you're just going to say python configure.py. And if you'd rather use invoke, we also have the invoke command. You can just say invoke configure, and that will execute the script the same way. All right. And this is, again, just a high level overview of what the actual script looks like from top to bottom. I've tried to include additional comments within the script as well, so that you can revisit it and have a local copy of what we're trying to do within each one of these steps along the way. And this is what the execution actually looks like. I've included a screenshot here for us. We issued python configure.py. At that point, we run the inventory function, which looks into our inventory YAML file. It stores all the router devices in a new object called devices. Then we pass that into the main function. And from there, we see that we first build the connection to the first device inside of our list. In my case, that was the router named CE1. Moving on to our next section, let's take a peek at the generate.py script. This script is very similar to the one that we just looked at, which was configure.py, but with one really big exception. With generate.py, we're only going to template the config and save it to the local file system. So if you don't have like a dedicated lab to test out the configure.py, but you still want to see Python generate the configs, generate.py is going to be the script for you. Now, it's going to be found in the same folder directory structure, so we're not going to revisit that topic here. But let's look at some of the differences within the code deep dive section. Starting off at the top, we can see that we're also going to be using the same inventory file that we did for configure.py. So we're not going to revisit this topic of importing YAML and how to safely load an inventory into a new object. We've covered that, so we feel confident with it. The difference here is, though, that instead of importing the libraries from PyEasy, specifically the device and the config class objects, this time we're just going to be importing Jinja 2, two main functionalities. One is environment and the other is file system loader. Environment will allow us to kind of define our Jinja 2 environment, right? It's like going into the settings menu inside of an application and clicking on some settings and turning some off. That's effectively what the environment is going to allow us to do. And the file system loader allows us to pass in a parameter as to which directory we want to be the root of our Jinja 2 templating. And so let's breeze over the inventory section, because again, we know what that actually does. And let's start here with some of the other options that we're configuring. The first of which is the output directory, right? And this is exactly what it sounds like. We're generating the configurations and we want to save them locally to a specific location. In this case, I'm creating an object called config path, and I'm setting it equal to a specific string. That string is the file directory structure that we want these configurations stored in. So in my local directory, that's what the ./ indicates at the left side of the string. I want my folder to be called configurations, and I want the subdirectory to be called generated, right? Now I'm storing this as a constant. That's why it's in all caps here. I could have very well just stored this as a regular variable. It's not that big of a deal. It's just constants are available throughout your Python functions, so you don't necessarily need to pass them as parameters. It's a convenience thing for me. And now it's time for us to adjust some of the settings of Jinja 2. The first thing that we're going to do is we're going to reference that environment class that we had imported at the top of our script, and we're going to pass in the file loader, which just points to the local directory here. We're also going to set a parameter to auto escape equals true. This is a security function and should be used whenever you're building something within Jinja 2. If you're interested in it, check out cross-site scripting in Jinja 2, and there's a lot of good, interesting read-ups on it. But for our case, we're just telling Jinja 2 where we would like to start our environment at, which is the local directory. I'm also changing two parameters or two functions within Jinja 2. One is trim blocks and the other is lstrip blocks. The only thing I want you to take away from these two parameters is it's helping us keep our outputted template file nice and concise, right? It cleans up a lot of the white space that would have been there otherwise. Now, much of the rest of this script is going to execute very similar to our configure.py script, where we're loading variables from a YAML file, we're running them through the same Jinja 2 template. The only real difference is that we're generating a local file instead of building a netconf connection to the remote device. So let's just focus in on that part here. What we see is we declare our Jinja 2 template, we declare our variables, and then we tell Jinja 2 we want to render a configuration. We're going to pass in our variables into the template, and then we're going to store it as an output of a file. And if there's any problem loading the YAML variables, we're going to get an error message here. So that's why we're including all this functionality in a try and accept clause. It'll try to do this, but if it runs into a YAML error, it will print out that error to the screen here. And as far as writing it to the local file, what we need to do is we need to tell Python, I want you to open a new file with write permissions. And then I want you to go through every line within our Jinja 2 template and strip out all the white space. Again, this is just an effort to make the output file really nice and clean here, rather than having a bunch of additional white space. That's effectively what we're doing here, and then we're writing that file to disk, and then we're printing out a message saying the configuration was built, and here's the name and path of the configuration file. Initialize script, this is exactly what I had said for the configure.py, so we won't revisit that. Let's take a look at the workflow. Again, same workflow, except we're just calling a different file here. And when we execute it, the only thing that we see take place is we print a message to the screen saying we have built a configuration, we've stored it in the configuration/generated file. Each device has its own unique configuration, and it's saved as hostname.conf. And here is just another glimpse at the script from top to bottom in case you're interested in revisiting that. So now that we've got the generate.py covered, let's quickly talk about rollback, and then we'll finish it up with the validation script, validate.py. Now the rollback script just allows us to roll back our configuration to the previous committed state. This is only really helpful if you're executing this script locally against a lab environment and you want to roll back any changes that you had just made to the device. Now, some interesting things here is that we're importing several different error messages from the PyEasy library into our script. There's several things that can go wrong whenever you're performing a configuration commit operation. And by importing these different types of error type messages, we can give the administrator or whoever is executing the script a lot of information as to what exactly went wrong and how to recover from it. So although it looks like we're importing a lot of new functionality, we're actually just importing 5 different types of error messages so that we can see an issue if it comes up here. And again, we're going to consume the same inventory file. You've seen this a couple times before, so we're just going to breeze on over it. And again, we're going to loop over all the devices within that inventory file. Here we can actually see the first of the error messages is being utilized. We're going to try to open a connection to a device, and if that proves to be problematic, we will get a connect error, which will print out to the terminal. We cannot connect to the device. It'll have its name, and it'll also include the error message. So really helpful for anyone that's running into connection problems, whether from firewall information, port numbers, username, passwords, those types of things. Now, for the bulk of our script here, again, we're going to use the configuration object that we inherited from the PyEasy library to grab an instance of the actual configuration and store it as an object here called configuration. Now that we have the configuration as an object, now we can do various functionalities upon that. One of which is to try to attempt to enter the exclusive configuration mode, which effectively is a configuration lock on the candidate configuration database. So we try to perform a lock. If there's a lock, we're all good. If we fail to get a lock, then a lock error message will be generated and will print out to the screen as well. Then we'll try to roll back a configuration, and the rollback ID in this case will be 1, right? Remember, the devices have a historical perspective of which changes happened at which time. We would typically reference this. You would say rollback 1, rollback 5, however many commits you want to roll back to. In our case, I'm just saying roll back to the previous committed, so that's rollback ID of 1, and then perform the configuration commit. But you can see we've got a commit error checking. So if there's any problem with our commit, we'll have that error message printed to the screen. We also have an RPC error. If we are unable to actually perform the rollback for any reason, we will also see that error message printed to the screen. Finally, we unlock the exclusive mode that we had on the database, and then we close out our connection. I don't know. Yeah, we do have some screenshots here. So executing this from the files/python directory, we just call python rollback.py. And here you can see the error messages, or actually just the print messages that we're printing to our console screen. In this case, connect to a device, we lock the config, we roll back the config to its previous iteration, we commit that, and then we exit and then move on to the next device. So not going to spend a whole lot of time on rollback. You may want this. You may think it's helpful in other use cases. So we've also included some extensive documentation within the script to help you get along with that as well. Moving over to the last one, which is one that I'm very excited about, and that's the validation script using Juniper's Jsnappy library. Now that we have the devices with the configuration, we want to make sure that the control plane is actually performing the role that we expect it to. And specifically what we want to look at is the status of our BGP neighbors. So what we have here is a tool called Jsnappy. We're going to import Jsnappy into a script. We're going to take a snapshot of the device's control plane, and we're going to run it against a test that we compile here. So Jsnappy requires a configuration file, and it requires a test file. The test file will be written in YAML, and it'll have things like what command we want and what specific object in the output we'd like to validate. And the config file will just tell the Jsnappy script where to find the remote devices and how to log into them, etc. So there's actually very little code that takes place here. Jsnappy will handle all the heavy lifting for us. So let's talk about this just again for a second. In the code deep dive, we're importing two different functionalities into here. One is the operating system. This will allow us to capture information about our operating system. Specifically, we're looking to understand where in the folder directory we are executing this script from. We have to have a reference point to our current working directory, and import OS is one of the ways that that's commonly done in Python. We're also importing the snap admin functionality from Jsnappy. Now this is going to allow us to take a snapshot on the control plane based on some kind of command that we're looking to validate against. So what this will actually look like, we're going to perform a couple of configurations. One, I'm going to create a new constant variable called PWD that stands for Path Working Directory, which is basically saying where are we in this, when we execute the script, which folder directory are we listed in. And we're setting that equal to as the output that you see here. This is a way in Python to just say current working directory, because who knows where you're executing this script from? It could be var temp, it could be your home directory, it could be your downloads folder. We don't know, but the Python script or Jsnappy, it needs to know. So this is a way for us to do that. Again, we're importing the object of snap admin. This is going to give us all the Jsnappy functionality, and we're saving it as another constant called Jsnappy. And we're also creating a constant called config, and we're setting it equal to this string that you see here. Now, the string is actually just a YAML representation embedded inside of a Python string, multi-line Python string. But you can see that PWD actually gets referred to right within the YAML markdown file. So wherever you're executing this from, let's say you're executing it from /var/temp within your file structure, this test would say /var/temp/test _ test L3VPN routes.yaml, right? And then again, the basic parameters of how to interact with our network devices. What's their IP address? What's their username and password? So these are the three configuration objects that we're going to set here. And here's an explanation in case my verbal reading didn't really help and you just want some text to actually read up upon. So that's going to be the three of the big configuration parameters within our Python script. Let's look at the actual Jsnappy test file. It's quite simple. At the end of the day, it's a YAML file, and at the top of the file, we tell the script just which test we would like to have ran. And these two tests will actually reside underneath this statement as well. So route table BGP L3VPN.0. This is this exact test right here, where we're going to be running this command, show route table BGP L3VPN.0. This looks in this specific routing table. And what we're looking for within this test is we want to make sure that the active route count is not equal to 0, right? So what are we saying? Saying Python SSH into this device over a netconf session. Look into the output of show route table BGP L3VPN, and then iterate over the results that come back and make sure that there is no instances where the active route count is 0. This must be greater than 0. Actually, it could be, technically it could be less than, but we all know that that's not possible in the routing table. It's either 0 or it's above that. So we're validating that we have routes in our L3VPN circuit. And if we do not, we're going to print a message out to the screen, right? And so this is the other test that we've included. You can see that we included this right up here. Route table customer 1 INET 0. Same idea, right? We're validating from the BGP adjacency to the customer. We're looking inside of that routing table that the customer is advertising to us, and we're making sure that the active route count is not 0. Right? It can be any number. It can be 1, we're happy. It can be 6,000, we're happy. It just cannot be 0. If it is 0, well, then we got a problem, and we'll alert to the screen. Now, this is what it actually looks like within the script itself. There's not a whole lot going on. Actually, let's just script down to the script here. Here's the full script within its entirety. As you can see, most of the parameters, they take up the majority of this script. The only thing we're actually doing inside of our secret Python clause here is we're saying, Jsnappy, take a snap check, meaning grab the current state of the device's operation state. And I want you to run these tests against this series of devices that we've declared right up here. Right? And this is the output of what it actually looks like when we run the validation script. So Jsnappy is going to produce back to the console, and it's going to say, hey, look, we're connecting to this device, we're running this command, and it'll give you green for passes, it'll give you red for failures. So in this case, we can see that the first test is going through where we're performing the route table BGP L3VPN. I could have named that something a lot easier. But what we see is the device, or the Jsnappy, comes back and says, hey, you know what? Active route count was not equal to 0, so you're good to go. And then it's going to perform the next test in line, which is the validation of the customer routing table. And it's going to say, hey, thumbs up, we got an active route count that is not equal to 0. And you'll get a nice little summary right up here. And then we log out of the device, and then we go and jump into the next device and perform the same type of operations. So again, Jsnappy is a open source Python tool that will allow you to validate the data within a device's router. This is unfortunately limited to Juniper devices. It technically could work for other network vendors that support operational RPC commands, or just have their output structured in XML. It could work for that as well. Unfortunately, as we all know it, most of the other vendors are still in the screen scraping world. And so getting this kind of structured data, especially for operational commands, it's just not possible inherently. You would have to build all of this by hand. But if you live in the Juniper world, you get like a really big easy button, and you can craft these types of validation tests for any type of thing that you're looking for. It doesn't have to be related to control plane. It could be validation of power supply status, or optical light levels on your SFPs, or really any type of command from a network device. You can run and build your network assertions, which makes Jsnappy so powerful. So I hope these code deep dives for these 4 specific scripts it's been helpful, that you understand how the actual automation is doing the task that it has. Again, my name is Calvin Remsburg. I would like to thank you for taking out so much of your time in order to sit here and learn something a little bit about Python, or maybe even MPLS L3VPNs. Should you run into any problems with the source code or just the project itself, please feel free to fill out an issues report here within the source code repository. It's the best way of getting my attention. But please keep an eye out for future installments within this series for different reference architectures. And if you have any suggestions or recommendations, again, just an issues report is the best way of getting in touch with me. Thanks again, and enjoy the rest of your day.